Okay, on to problem number 5. So this is instruction scheduling and register allocation, so back-end stuff. So the first part is assume that a CPU can execute one addition and one multiplication in each cycle. Produce a schedule for the following code that will more effectively use the CPU's hardware. 3 points. So we talked about this in class on Wednesday. And what we were looking at is the dependence graph of the problem. So we might want to sort of write this out and see what that dependence graph is. So let's say W equals W plus 5. That's our first one. We may want to put this into SSA, though it's not going to be super necessary for such a small problem. X equals W plus 2. That's dependent on the W equals W plus 5 because that creates a new value and then we use it. Y equals V times 3. That's not dependent on anything yet. And then Z equals W times 4. So Z equals W times 4 as our last instruction. So from our dependence graph, we can see that we've got the chain here, W equals W plus 5. That leads into two different instructions. And then we've got this sort of rogue Y equals V times 3 over there that doesn't need to do anything or doesn't need to rely on anything. So assume the CPU can execute one addition and one multiplication in each cycle. We're assuming it's superscalar. It can run two instructions at a time. So we're going to want to do W equals W plus 5 first because that is the most, that's the instruction that's dependent on the most things, right? So that's the first thing we want to do. And then we can execute this Y equals V times 3 at the same time because it's not dependent on the first instruction. Therefore, we can do it immediately. And then after that, we can do the two instructions that are dependent on the value of W. We can assume that it's been produced at that point. So Z equals W times 4. And that's our code. So that's the quick way to sort of reschedule that. We build a dependence graph, and then we select instructions based on this greedy heuristic of how long the chain is for that particular instruction. So part B, using the optimized code from the previous problem, draw an interference graph and label each node with a number indicating the color of that node. Assume that X, Y, and Z are live out and V and W are live in. So this is what we did for graph coloring. We're going to have, we can draw our sort of live in V and W. We can write our code down again. So W equals W plus 5. Y equals V times 3. X equals W plus 5. W plus 2. I can't read my own writing. And then Z equals W times 4. And then live out, we'll just say out, is X, Y, and Z. And the important thing there is we need to keep those values there, right? So those are our values. We're starting with V and W, so we'll say V starts here, and we got to figure out where V is done, which is right there. W is also live in. W is used until the very end, so it's going to go there. X is not live in. X gets used first here, and it is live out, so we're not going to end it. Y starts here, and it is live out. And Z starts at the bottom here. It is live out. Okay. So keep in mind, the reason we're drawing these circles is that we can, potentially reuse where W was to put it, put Z in that register. We can reuse where V was and put Y in that register if it works out that way. So now let's draw our graph. So we've got V, W, X, Y, and Z. So we need nodes for each of those things. And we are going to draw lines for each variable based on what it interferes with. So V and W are live at the same time. That means they can't have the same color. That is the only thing that V is live with is W, because the only operation that happens while it's live is W equals W plus 5. W, we already have a line to V. It is also live at the same time as Y, so W needs a line to Y. It is not live at the same time, or it is also live at the same time as X because we need to keep it until Z pops up. So W is going to have a line to X, and then it can be reused by Z, so we don't need it there. X has a line to Y. It's live at the same time, and it has a line to Z. So it's live at the same time. And then Z has aligned to W, and or W has aligned, or Y has aligned to Z, or Z has aligned to Y. Because those are the last two things, and they are interfering with each other. So that's our interference graph. We can, use some heuristics and choose maybe the fact that like W, X, and Y are sort of heavily linked here. We can see that those are probably going to need different colors, and so we could use red, green, blue, and then we can start labeling the other two nodes. So let's try to label Z. It can't be green or blue, but it can be red. And that's sort of what we saw, might happen is that W sort of ends and it can give its, place to Z. And then V, since we see that it's going to be linked to Y, V can actually take anything that's not red, but we'll say maybe that, Y is going to take the value from V, so we'll give V blue. And so, then we could, maybe it would have been better to just label these as registers, but we could say that blue equals, R0, red equals R1, and green equals R2 if we want to be pedantic about it. We could also rewrite this code to actually register allocate it by just substituting in based on the color that's there. So it's a bit of a long one, but let's go on to the true false for this problem that we're attached here. So true or false, static scope available to the compiler is larger than dynamic scope available to the hardware. False. That's the reason we use out-of-order processors, because we can have 512 entries with dynamic control flow, branch prediction, all sorts of stuff happening in the hardware that we don't have at compile time. Usually our static scope is pretty limited. Next up, instruction scheduling and register allocation are NP complete. That is true. Because we talked about it. That's those problems, right? Graph coloring and picking out the schedule. Those are just guess and hope you get the right answer. Do some sort of greedy algorithm and or try every possible option. Superscalar processor executes more than one instruction at a time. True. That's what we talked about again. It's just the definition of superscalar here. It's safe to reorder dependent operations. False. If it depends on something, like if we look at, Z equals W plus 4, it's not safe to do that before W equals W plus 5, because that is what the programmer said has to happen first. We're assuming that that is the case, and we can't just change it on them. Function inline decreases the static scope available to instruction selection. That is false. It actually increases the static scope, right? Because we are putting more code into the body of a basic block, and therefore instruction selection has more instructions to work with. And then finally, out-of-order execution negates the need for static instruction scheduling. That's also false. And there are things like, embedded processors that don't have a heavy out-of-order core. Out-of-order tends to be very power hungry, so low power systems. And just in general, there is some benefit to scheduling things in the right order in the first place, so that once they get into the processor doesn't necessarily have to do quite as much work. So that is it for problem 5. That was a long one.